Welcome, everyone. The inner ear. It's just the most complex sensory organ we have. And over the next two parts, we are going to unpack how it literally builds itself from scratch. Today, we're starting at the very beginning with the otic placode and the genetic trigger that kicks everything off. Then, in part two, we'll get into the really cool stuff, cochlear coiling and the organ of Corti.
So yeah, let's just dive right in. For this explainer, we are honing in on that absolute first step, the initial command and the incredible genetic cascade that turns a few simple cells into the foundation for the entire inner ear.
And really, this is the core question, isn't it? How on earth does a seemingly plain little patch of embryonic tissue, what's basically skin, get the instructions to build something as ridiculously precise as our hearing and balance system? It's just a phenomenal piece of biological engineering.
Okay, so this is where our story begins, with the otic placode. Now, the key thing to remember here, the most crucial point, is its origin. This is pure surface ectoderm. Nothing else. No other embryonic layers. Not the mesoderm that makes muscle, not the endoderm that makes your gut. None of them contribute to the actual sensory parts. It all comes from this one simple thickening. That exclusivity, that's the foundational fact for everything that follows.
So, if this patch of ectoderm is going to become an ear, it obviously can't just decide that on its own. It needs a command, right? An external signal. And that signal comes from its very influential next-door neighbor, the developing brain.
And you know, this happens incredibly early in development. We're talking around day 22 of gestation. The embryo is just a couple of millimeters long, and get this, the neural tube isn't even fully closed yet. But right then, the first sign of the ear appears. Two placodes, one on each side, pop up right next to a specific part of the hindbrain called the rhombencephalon.
Now, what's really fascinating here is the precision of these signals. These aren't just vague suggestions, they are very specific molecular orders. The hindbrain from rhombomeres 5 and 6 starts secreting a protein called FGF3. At the same time, you've got WN signals coming from the dorsal neural tube, and another signal, FGF10, from the mesoderm right next door. It's this specific cocktail of chemicals that basically points to the ectoderm and says, you, right here, you're going to build an ear.
Okay, so once those cells receive their marching orders, they don't just, change their shape. They flick on a whole complex internal genetic program. They literally start reading from a blueprint titled How to Build an Inner Ear.
And one of the very first, most critical genes to get switched on is PAX2. You can think of it like a master switch. When those FGF and Wnt signals flip this PAX2 switch, it triggers this huge cascade of hundreds of other genes, all part of that Build an Ear program.
And here's where we see just how critical a single gene can be. When PAX2 is mutated, it causes something called renal colobus syndrome. Now, the name itself tells you the gene's job isn't limited to the ear. It's also vital for developing kidneys and eyes. The fact that one single gene mutation causes defects in all three, kidneys, eyes, and ears, is absolute proof of how fundamental PAX2 is.
All right, another master gene that gets activated by those initial signals is EAY1. And just like PAX2, it's a transcription factor, basically a protein that tells other genes when it's their turn to turn on or off. It works right alongside PAX2 to carry out the genetic game plan.
And again, just like with PAX2, we see these major clinical consequences when EYA1 isn't working right. Mutations here cause branchioautorenal syndrome, or BOR, and once again the name tells the whole story. It messes with the branchial arches, the ear, that's the oto part, and the kidneys, the renal part. It's a great example of how the embryo reuses these powerful master genes to build multiple, seemingly unrelated parts of the body.
So, how does all this genetic activity actually lead to a physical change? Well, with the blueprint now active, the placode begins this incredible transformation. It doesn't grow out, it dives in.
This whole process happens in a few really clear steps. First, you have the placode, that flat thickening. Then it starts to buckle inward, forming what we call the otic pit. You can kind of imagine it like pushing your finger into a soft piece of dough. That pit just keeps getting deeper and deeper until the edges at the top touch and fuse together, pinching it off completely from the surface. And what you're left with is the otocyst, this self-contained hollow ball of cells, now buried deep beneath the skin.
And this all happens ridiculously fast. By about day 30, so just a little over a week after the placode even showed up, this whole invagination and pinching off process is done. The otocyst is now a totally independent structure, and it's ready for the next phase of its mission.
But this little sphere isn't just sitting around waiting. No, even as it was forming, its cells were already getting to work on their specialized function. They start to create this completely unique internal environment, a kind of private inner ocean.
This fluid that's filling up the otocyst is the precursor to what will become endolymph. And I'm telling you, this stuff is bizarre. Its chemical makeup is completely unlike any other fluid found outside of a cell anywhere in the body. The cells making up the otocyst wall are actively pumping ions to create this very, very special liquid.
And the most shocking part? Its potassium concentration. We're talking about 150 milliequivalents per liter. Now, to give you some perspective, that's almost identical to the potassium concentration inside of our cells, not outside. And this detail is absolutely crucial for how hearing is eventually going to work.
So this is the main takeaway here, this ionic paradox. Literally every other fluid outside of cells in your body, blood plasma, cerebrospinal fluid, you name it, is high in sodium and low in potassium. The otocyst does the exact opposite. It creates this wild high potassium, low sodium world. And what that does is establish an incredible electrochemical gradient that down the line will be the battery that powers the hair cells of the cochlea.
And just as a quick aside, if you're finding this kind of detailed breakdown helpful, please do like and subscribe. We create these custom medical videos just for you. Okay, moving on to our final point.
So let's wrap up this first part here. We've journeyed from a simple patch of skin to this amazing hollow sphere of cells, the independent otocyst. It is now armed with a totally unique internal ocean and a complete genetic blueprint. It's fully programmed and ready for its next monumental task, to elongate, twist, and differentiate into the cochlea and the organ of Corti. And we'll see exactly how it pulls that off in part 2.
All right, welcome. Today, we're diving deep into the development of the ear. We're going to cover the origins of those tiny middle ear bones and later how the ear canal itself is formed. But first, let's start with a really fascinating anatomical mystery that goes all the way back to our earliest days as an embryo. You know, when you look at the middle ear, it seems like this perfectly designed little machine. But there's this one detail, one tiny little inconsistency that has totally puzzled medical students for generations. It just doesn't seem to add up. So here's the deal. You've got these 3 little bones, the ossicles, that have to work together perfectly as a single unit. But get this, the first 2, the malleus and incus, are wired up to the trigeminal nerve. That's the nerve for chewing. And the third bone, the stapes, is connected to the facial nerve, which is for, facial expressions. How does that even make sense? To get the answer, we can't look at the finished product. We have to go back, way back, to the original blueprint. To solve this riddle, we've got to travel back in time, just a few weeks into development, and take a look at the absolute fundamental building blocks of our head and neck. And this right here is the master plan, the branchial apparatus. The best way to think about it is like a set of paired construction crews, lined up on either side of the developing throat. Now for our middle ear mystery, we really only need to care about the first 2 crews, the first and the second branchial arches. And this is where things get really cool. These 2 crews, they don't just split the job 50-50. They do it in a very specific way. The first arch crew, they build the main parts of the first 2 bones. But then look at the second arch crew. They build the entire stapes. And then they also chip in to build the little connecting pieces for the other 2. It's a true joint project. And that right there is the key to this whole thing. This whole shared constriction job idea, well, that's our smoking gun. It's the one clue that just blows this case wide open. So let's connect this back to the nerves and finally solve this puzzle. And here it is. In embryology, there's this one simple, unbreakable rule. Each branchial arch, each one of those construction crews, has its very own dedicated foramen. And that foramen is a specific cranial nerve. And that nerve follows every single thing its arch builds, no matter where it ends up in the adult body. So that's the fundamental law of development that solves everything. The malleus and incus are tied to the trigeminal nerve because they were built by the first arch crew. And the stapes is tied to the facial nerve because it was built by the second arch crew. It's got nothing to do with their final function. It's all about their origin. Mystery solved. It's really insights like this, connecting the basic science to what we see in the clinic, that are just so important. If you find this kind of thing helpful, definitely like and subscribe for more. Okay, so we've figured out the bones and their nerves, but these bones can't just float in empty space. They need a room to work in. So next up, let's see how the body actually carves out that space, the middle ear itself. Okay, so these ossicles are amazing little pieces of engineering, right? But they can't transmit sound in a vacuum. They need a space, a cavity to vibrate in. And just like the bones, that space, the middle ear cavity, has its own very specific origin story. The whole middle ear space starts out as this internal pocket of tissue called the first pharyngeal pouch. This little pouch starts to grow outward, and the very end of it expands like a balloon. That's what forms the primitive middle ear. The part connecting it back stays narrow, and that becomes the eustachian tube. And that, by the way, is exactly why your middle ear is connected to the back of your throat and why it's lined with the same kind of tissue as your respiratory system. It's literally an outgrowth of the primitive throat. So, why does all this embryology matter to a clinician today? I mean, this is all ancient history, right? Well, not at all. Because this developmental blueprint, it gives us an incredibly powerful map for predicting and understanding congenital malformations. And this right here is the clinical payoff. It's huge. If you have a patient with a condition that affects the first branchial arch, something like Treacher-Collins syndrome, you know exactly what to look for: problems with the malleus and incus. And on the flip side, if a surgeon goes in and sees a problem with the stapes, a huge alarm bell goes off. Because they know the stapes was built by that second arch crew, which means its foreman, the facial nerve, is probably taking a weird route nearby. And that is absolutely critical information to have before you operate. So, the ultimate takeaway here is that embryology isn't just about the past. It's a living, breathing, predictive tool. It allows clinicians to understand the patterns of what can go wrong, to anticipate challenges in the operating room, and ultimately to provide better care for patients. It's a map that connects our very first cells to the person we become.